morning. So thank you, organizers, for putting up this this beautiful conference. And I have to apologize in advance for the mode of presentation. So I decided to combine impersonal nature of slides with my horrible handwriting that will be on full display. And this is a joint ongoing project, long-term project with Misha Shapiro, who's here, and Alec Weinstein from Haifa. It doesn't mention the Docker integrable systems at all, but I think the integrable system community is a community that really appreciates good coordinates. And well, I'm going to talk about cluster structures and cluster algebra, a series all about good coordinates. So objects where we're going to look for cluster structures are Poisson-Lie groups, which support many well-known integrable systems, various versions of Toda flows and some, well, pentagram map, and all of them, well, many of them, or discrete versions of them, can be realized as sequences of cluster transformation. I'm not going to define in full detail cluster algebras, but I'll try to explain what cluster structures are about from our point of view. So what are they? So let's, oh, what happened here? Sorry. Yeah. Okay, so I'm, yeah, let me, I think the format it changed here. Okay, I'm going to talk. Yeah, I can. Yeah, I can use a board here, but actually, let me just say it in words. So, yeah, it will be fine after this slide, I think. So we have a Poisson variety that we prefer to admit a toric action, and we try to construct a family of nice coordinate systems there. And nice in our context means that there is a Poisson bracket, but for each couple of coordinates in this coordinate system, the Poisson bracket is very simple. It's just a constant times a product of this coordinates. We also want these coordinates to be regular functions on our Poisson variety, and we want any two of these coordinate charts to be connected by a very simple sequence of transformations, birational transformations. And on top of that, we would like to have the following. We want to have enough of this coordinate chart so that, in fact, so if you generate algebra from all the functions that are involved in all of this coordinate system, we want any regular, the ring of regular function to coincide with this algebra. So let me just try to go to a main example, maybe that will be relevant to us. So one example of such situation is due to Bernstein, Fomin, Zolovinsky in their cluster algebra 3 paper. And what they did, they introduced cluster structure on double Brouillard cells of a simple Lie group. We will concentrate just on the open double Brouillard cell, so I don't need a definition of a double Brouillard cell for that, but just imagine that you have a simple Lie group. Let's just take, for the sake of this talk, GLN. And so what are these coordinate systems we're talking about? Well, the coordinate systems, these charts, which we'll call cluster, are made of very nice functions. Many of them are just made out of minors if we're talking about GLN, or generalized minors if we're talking about other simple Lie groups. So all coordinates that we obtain in this way are regular functions on our group. And then, so this cluster structure is complete. So yeah, I will give a detailed example in the next slide. As I said, so ring of regular functions is isomorphic to cluster algebra, or slightly more general object called upper cluster algebra. And what's important for us here is that they are all compatible in this sense with the standard Poisson-Lie structure on the group G. So the group Poisson, simply groups have this nice quadratic Poisson structures, which are responsible for integrability of many systems. In fact, we saw one of these structures in Sasha Mikhailov's talk, this quadratic structure for the total length. So what is a standard Poisson-Lie structure? So there are many ways to characterize it, but I think the most transparent one is that is the following. So we have, let's just consider just triangular, 2x2 triangular groups, upper and lower triangular, just with coordinates A and B, and a very simple Poisson bracket of this sort. I can embed this subgroups into GLN in the following ways. This is a canonical embedding. And so what I require is that this embedding is Poisson. It's one of the many ways to describe this quadratic Poisson structure. But if you write it down in coordinates on GLN, it will not be as simple. And another property of the structure is that it reflects combinatorics of the corresponding file group. So what does that mean? So there is this nice parameterization, again, due to Lustig and Fomin, Bernstein, Zelevinsky, which works as following. So I take many copies of lower triangular 2x2 matrices, many copies of upper triangular. How many? Well, this is the length of the longest file group element. And then I take a maximal torus Cartan, and then I consider the following map. I just take the product of this embeddings described above, dictated by a reduced word for two reduced words for W0. Just multiply them together, multiply by element of the Cartan. This will end up in I group G, and this will sweep out open dense subset inside of G. So this is parameterization. So this class structure is compatible both with combinatorics of associated while group and with a Poisson-Lie bracket. So this is all rather abstract. So let me just give you an example of how this works. So maybe it will explain some basics about cluster structures as well. So cluster algebras, cluster structures, they grow from seeds. So what is a seed? You start with this one coordinate chart or one collection of variables, one collection of functions on your object, and there is some combinatorial rules that allows you to transform this coordinate. Combinatorial rule is given in terms of the quiver. So here's an example. I'm talking about GL4. So I will have to start with a family of 16 functions, and combinatorial rule quiver is given by this picture. And in this case, it is convenient actually to describe both functions and the quiver on the same picture. So what are my functions? The functions are given as just maximal dense minors with a particular entry xij in the upper left corner. And I place this function at the vertex of my quiver, which is labeled by the same I and j. So if here is this Fij is just a minor in this example with rows 2, 3 and columns 3, 4. All right. And what I'm allowed to do with this function is transform them according to the rules of cluster transformation. So I can transform one function at a time. I take a vertex in my quiver. I consider all the arrows that points to this vertex, and then multiply all the variables which corresponds to those vertices. Plus another monomial is given by the product of all coordinates or coordinates of all vertices to which my selected vertex points. Okay, so that's a cluster transformation. So I consider that the new function is given by the equation there in the corner. And it may look strange, but we all have seen this formulas all over the mathematics. If you think of short-Klucker relations, Jacobi identity, Ptolemy relations in both hyperbolic and Euclidean geometry, they look like that. The strange part is what happens to the quiver after that. And so I just going to give it by example instead of giving precise definition. So what happens? So again, I have to transform this quiver locally. And what I do is whenever there is a directed path through my vertex, directed to pass, I add a shortcut, so going straight through. This will force me to actually add shortcuts here as well. But there is a rule that whenever I have two cycles, I'll just erase it. So this arrow disappear. And then I reverse all the arrows at the vertex. And this rule looks very strange. It was invented by Fomin and Zelevinsky to, well, for definitional cluster algebras to work. And this was also a reason for Misha, Alec, and I to start looking at this, because we wanted to explain it geometrically. And what it is geometrically, well, we had the Poisson, underlying Poisson structure. I changed coordinates. This is what happens when you change the coordinates. Right? This is just rewriting the same Poisson structure in different coordinates. So what are the properties here? Well, all the properties that we want. So even though the transformation involves division, all new functions will be regular, and this is consequence again of Kluge relations and other determinantal identities. It is complete. So if I start mutating, so I can repeat this process. I can mutate and mutate and mutate. I will obtain a gazillion of functions, and among them, I will get every matrix entry. So the ring of regular function will be inside this cluster algebra, but since it's the cluster algebra itself made of regular functions, they will coincide. And it is compatible with a Poisson bracket. So what it means is that if I consider this Poisson-Lie structure on the group GL4 or GLN, then a compute bracket between any of these Fij's, then it will have this simple form as here. And the reason for that, it can be assembled from these elementary pieces, which obviously have this problem. All right. There are some other nice features that, for example, this cluster structure descends naturally on cluster structures on upper triangular and lower triangular matrices. It's actually very easy to do. You just take this quiver and just cut it in half. You'll have upper triangular matrices living above and low below. All right, so, and it will be compatible with just Gauss factorization. Gauss factorization. I guess I'll have to hold this. All right. So okay. So how standard this cluster structure is? So I made some choices, but there was a standard Poisson-Lie bracket, and then one may think that well, once you are given a group, your cluster structure on it is unique. So let's just explore that. So I'm going to modify this picture just a little bit. What I'm going to do is take one of the functions that we had before. So before, according to our rule here, there would be just element x for 1, just a minor. And I replace this function with a strange function, which is not a minor at all. It looks like a minor, but it's not. If you look at, there is a shift in indices in the row. Okay, so this was frozen. I replaced it with a new function, and I updated the quiver somehow. Well, I didn't give you any reason for doing that, but I claim that most of the nice properties will be preserved. It is still a regular structure, even though, well, you cannot directly apply Kluge, but you can apply it to some other object. It is still complete, so you can restore in a natural way all the regular functions. But what about Poisson bracket? What is it compatible with now? Because we destroyed the nice features that we had before. And it no longer restricts to up and low barrel. So either we have to forget about this property, or we have to update the notion of upper and lower barrel corresponding to this case. And we can do it again, and we can make it even stranger. So now I'm going to take several nice functions, minors that were sitting here, and replace them with strange functions which are described above. So I'll consider this strange block matrix, and I will replace functions sitting in all these vertices with principal minors indicated in the picture. And again, it remains regular. And again, it remains complete. And again, it's not clear what this structure compatible with if we're talking about Poisson brackets. Okay, so what's going on here? Of course, I am cheating a little bit. These examples were not invented just this way. We actually started with Poisson bracket, and we wanted to look for structures compatible with something which is different than the standard Poisson bracket. And to talk about this, maybe I have to describe a general strategy. So let's talk about compatibility of cluster and Poisson structure. So let's go back to general setup. Again, let's consider Poisson variety, and suppose we manage to find a nice coordinate chart with this what we call log canonical property. And from that, we need to build an initial cluster, right? Initial clusters, well, initial rules of transformation, which are described by the quiver. So we need to find how to construct this quiver. And it's actually quite easy. Quiver corresponds to adjacency matrix, skew-symmetric matrix. We have another skew-symmetric matrix, which is given by the structure constant of our Poisson bracket. And all we need to do is find something which, so such that adjacency matrix multiplied by the structure matrix of Poisson bracket has this nice property. And if in addition we do have a toric action on our variety and we require that all our coordinates are homogeneous with respect to this action and will remain homogeneous after transformation, then this quiver Q is defined uniquely up to scaling. And yes, omega is not zero. Omega has to have some non-degeneracy property, some mild non-degenerate. Well, let's just assume it's non-degenerate, so that this BQ is of maximal rank. So this is mild condition. But this condition propagates. If I'll now use this Q and start mutating, then this condition will propagate. And so I will start building this new coordinate charts for my variety. And so so this is a general setup, and of course there is a question number one: how do you find this initial coordinate system, which is very ad hoc? And then completeness is also difficult usually to prove, but here are some important cases. And so most important cases, and they are Poisson-Lie groups. So Poisson-Lie group is a group with a Poisson structure such the product is a Poisson map, and Poisson homogeneous spaces. And this is Poisson variety on which a Poisson-Lie group acts, and that the action map is a Poisson. All right. And in most of the examples of cluster structure, most of the examples of cluster varieties, you have this action of a Poisson-Lie group present one way or another. Even you consider Grassmannian, Teichmüller spaces, Haidt-Teichmüller spaces, it is present there. So we're interested in a particular case of these two main examples, and so I'll have to talk about this particular case, and this concerns Belavin-Ginzel classification of certain class of Poisson-Lie structures on simple Lie groups. So I am not going to give full details, but I want to describe at least combinatorial part of this classification. So how does it work? So we have a simple Lie group. We have corresponding root system. We select two isometric subsets of simple positive roots and map that sends one of these subsets into another. And there is important property of nilpotency. Nilpotent means, so what do we do? We take a root that sits in gamma 1, little gamma sends it to gamma 2. It may lie in the intersection. So little gamma will send it again to something, and then eventually we want the image to get out of gamma 1. That's nilpotency. And there is another piece of data which is element of the tensor square of the Cartan, which is a solution to a linear equation which is determined by this gamma. I don't want to write this equation, but from this data one builds so-called R matrix, which is a solution to classic Yang-Baxter equation. And it has Cartan part R0, so this solution lives in the tensor square of the corresponding Lie algebra, and I can just write it down explicitly what the solution is. But Belavin and Drinfeld, what they proved is that any solution, quasi-triangular so-called solution to classical Young-Buster equation up to isomorphism corresponds to automorphism corresponds to this. All right, so you have here action of gamma on actually root vectors, which is naturally defined. It extends from positive roots to all roots, but here's the formula. And where is the Poisson bracket? So we can write it down in the following way. So there is this what used to be called Leningrad notation, and now I guess it's called St. Petersburg notation. I don't know how we should call it now, but anyways, it's this is just a notation. So let's imagine we're in GLN. This is just a notation for all the brackets between all the matrix entries. This is how many of them we should have, right? The size is equal to the size of element of a tensor square. And this is actually a formula for that, just commutator of our constant matrix R with x tensor x. So this is a quadratic bracket, which may be quite complicated. So natural coordinates are not at all of this particular shape. And there is a generalization of that. We can also consider on the same group of Poisson homogeneous brackets, which are given by a similar equation. But now we have two R matrices, one on the left, one on the right. And what it corresponds to is such a Poisson structure on the group that if I have Poisson-Lie group G, the same group acting on the left and on the right, then the middle is Poisson homogeneous. So it's a natural thing to consider. All right. And so so we're interested now in whether or not there are cluster structures compatible with that in this full generality, not the ones, the standard ones that I've shown you before, but compatible with this rich family of Poisson structures on our group G. And we had a conjecture which states that for any pair of Belavin-Drinfeld data, there exists a compatible, regular, complete cluster structure. Well, sometimes we'll have to consider generalized cluster structure. Remember, cluster transformation was old variables times new variables, a sum of two monomials. Sometimes we need more than two, but this will not be present in this talk. So this was our conjecture. We considered many different cases, and then we worked hard and managed to prove it for so-called oriented aperiodic Belavin-Drinfeld data. So I'll probably have to explain what this means. So what is oriented? So let me just try to explain it in AN case. So here's an example of A3, and I have two subsets of roots, and this is a map. So roots alpha 1 goes to alpha 2 goes to alpha 3. And this is oriented well because in A-type, isometry is given. So we have any subset of roots that is given by a collection of intervals. So if two things are isometric, we have to have collections of disjoint intervals of the same size. And oriented just means that, well, alpha 1, alpha 2, well, the order doesn't switch. So this is oriented, this is non-oriented. Aperiodic is a little stranger. And well, first of all, I have to apologize for the name. It should have been called acyclic, but in cluster series, there is something else which is called acyclic. So this is called aperiodic, and then it becomes even worse because this one is not even a word, but I have to use it. So non-aperiodic, but whatever it is. So here's the meaning. So this is what we do. It may look strange, but actually it's a natural object. So again, I have two copies of my Dynkin diagram. I described my collection of what is gamma 1 and gamma 2, and then I have this arc. What do they represent? They represent the action of minus W0 on simple root. So it's a natural action. But in A-type, you can actually draw this nice graph, and it may have cycles or not. And so if it does not have cycles, that is aperiodic, and if it does, like here, then it is this horrible. It has this horrible name, but well, we'll come with a better one later. All right, so so this is what we did. We proved this theorem. Maybe I should show you by example how this works. So here's an example. So I'm an SL5. I have gamma 1, gamma 2 consisting of 2 roots. And I want to, so what I need to do at least give you initial system of coordinates, which will have this nice Poisson brackets with respect to this complicated quadratic bracket. And here's the answer, and it looks very strange, but it works. So I will build out of these pictures. There is combinatorial rule, which allows me to build several these block matrices made out of sub matrices of initial element X. They are glued, if you look carefully, they are glued along the intervals that correspond to our beloved GLF data. Then out of these things, if you count how many, well, add up the sizes of these matrices, you will notice it's equal to 25. I need 25 coordinates. I will consider trade-on principal minors of all these 3 things. And those will be my functions. And they, for some reason, have nice Poisson algebra. And how do I place them in the quiver? Remember, my quiver was a square grid. And actually, it's also very convenient. If you pay close attention, you will find out that each of this function is a minor of this horrible matrix, and it has something in the upper left corner. And each pair of indices will appear exactly once. So I know exactly how to place them in the quiver. The quiver actually is not going to be that different. So something is going on here, but for a long time, we didn't know what. So we found an answer, we found a proof. And so let me go immediately criticize our own work. So first of all, definition of initial cluster, you will agree, is very ad hoc. Then there is a lack of explicitly theoretic meaning of this construction. And then compatibility with Poisson structure, so computation of Poisson brackets was just horrible, right? It's just horrible long computation, and we couldn't even do it in the group itself. We had to go to the Drinfeld double, compute brackets there, and then restrict. Well, it's not all, did not all go to waste, because that allows us to find the cluster structure in the Drinfeld double of G, and instead, and then my graduate student Dima Voloshin extended it for this more exotic situation. But we want to fix this. We want this to be a natural construction, or at least more natural construction. And so how one can do it? So it would be much better to use factorization in the style of Bernstein, Fomin, Zolovinsky. Just factorize element in your group and into nice products of naturally defined subgroups, and then maybe something will work there. But it doesn't work literally. We can also use the nice fact that in this Poisson homogeneous case, if I take structures corresponding to left and right R matrices R and R prime, and then another one was R prime and R2 prime, and consider just multiplication map, it's also going to be Poisson, and it will lead us into, so there is this nice functorial property into a structure corresponding to R and R double prime. So all these features need to be. And so how to solve this? So this is, the hint was actually in our initial proof of existence of a cluster structure, and this is how it was. So so we have this strange construction of functions, but the quiver looks almost the same. If it looks almost the same, I can pretend that functions sitting at the vertices are still just usual normal minors of matrices. And from them, I can restore another element of my group G. And there is no reason in principle that the result will be a nice map from G to G, but in fact it is. It turned out that it is, we defined it inductively, but it is a birational map. Okay, so again, it must have a meaning. And so we started looking for this meaning. The map is very nice. It's just, so again, I take this strange cluster structure. I pretend that the functions sitting at vertices are minors of some other element. I restore this element, and it turned out that the initial one and this new one, very simple birational transform. Well, no, not very simple, but at least a birational transformation. So here's a new recipe. And well, this will be a little involved, but I will explain everything. So let's just do a one-sided case first, because it will be easier to explain. So just imagine that we have this Poisson homogeneous structure with some R matrix is involved on the left and the standard one on the right. Okay, and so I take my element X of my group and then consider the usual Gauss factorization, low triangular, diagonal, upper triangular. But then I will additionally factorize the low triangular part. So how can we do this? So there is this Bernstein, again, Fomin-Zalevinsky factorization, which is, well, which respects reduced word decomposition of the longest element of the while group, and we can have we have control over the choice of this reduced decomposition, and so we can do it in the following way. We can consider reduced word, which such that W0, the longest element, factors in the following way. It's still reduced decomposition, but initially we start with the part of this decomposition is again the longest word, but in a Levy component that corresponds to the root system gamma 1, right? So just imagine that, well, the longest permutation is anti-diagonal, and we have these blocks, and we consider anti-diagonal in each block. So this factorization is unique. And okay, and so what do we do? And then this is where twisted in the title comes from, and then we take this first factor and apply a twist to it. So this is lower triangular. I will multiply it by this smaller while group element, and then factor it into upper diagonal and lower, and take the upper part. Okay. So if you do that, you can construct the following map, which I will show. Well, which I have actually shown above. Here's the map. So I take this element X, use this factorization, take this part, consider the twist, and then apply my Belavin-Greenfield map gamma to this twist, and then with an inverse map, right? So it is a map into itself, and the claim is that it is a Poisson map, which actually straightens up Belavin-Greenfield data. So it was it is a Poisson map into a standard Poisson-Lie structure. Okay. And if I have a Poisson map into a standard structure, and in the standard structure I have this nice coordinate system made out of minors, I can pull back those functions, and if I'm lucky, if this map is nice, then I can I will get nice Poisson properties. This will be not my nice initial cluster. Okay, and so so here's a statement. So this map is Poisson, and so yeah, as I said, I can pull back this nice coordinates for the standard structure to obtain also nice coordinate for non-standard structure. All right, so let's just let me show how this works for our favorite cluster. So in the standard case, so X hat lives in a standard Poisson structure, so nice coordinates made out of minors. When I pull them back, then I will get the strange block matrices that we've seen before. But now, well, they appear natural. This is a result of the computation. All right. So, all right. So let's see what happens if we, well, consider two-sided situation. So in full generality, when I have Poisson homogeneous structures that corresponds to both action on the right and on the left by Poisson-Lie group with non-trivial Belavin-Greenfield data. So here situation is a little bit more complicated, or maybe not a little bit more. So let's see what we have to do now. Again, I consider Gauss factorization, lower barrel, Cartan, upper barrel, and then I will factor both the lower and upper part in such a way that it respects Belavin-Greenfield data. So again, I have something that corresponds to gamma 1 on the left and gamma 2 on the right. And then I have two different twists. I have to define two different twists. One is the same as I defined before. One on the right, so I multiply by the longest while element on the other side. I consider the opposite Gauss factorization, and and then takes a low barrel part, and then now this looks complicated. So then I have to build this map rho L and rho R in the following way. So once we computed the twist, we plug it into powers of our beloved Greenfield map gamma. And this is when nilpotency work, because it looks like an infinite product, but it is not. So again, it looks like something quite horrible. And if you can write down equation, it is horrible, but at least it is defined type independent. It's now defined at least theoretically. And the theorem is that this is indeed a Poisson map from the standard now structure to non-standard one. But now it goes in the opposite way. So now if I want to pull back nice function from the standard structure, I need a map in the opposite direction. So this one looks quite horrible, and we need to know whether or not we will be able to actually. Okay, and so, well, I can talk about this. So in fact, sometimes we can. So this is where aperiodicity is important. So for aperiodic pair, so remember when we had this strange graph with no cycles, this map is in fact birational. It produces an initial cluster with, well, you can explicitly compute its inverse. And otherwise, we need to use a different technology, and the structure becomes generalized cluster structure, but then something interesting happens too, because it corresponds to considering symplectic leaves in this Poisson-Lie groups, which are parameterized not just by combinatorial data, but by certain conjugacy classes of subgroups. I will give you an example. So let's go back to examples that we have seen before, because here I can kind of describe the inverse of the map explicitly. So we had this ad hoc solution of our problem for the case of SL5 with this beloved Greenfield data, and I had this, unjustified long matrices. I claim that within this picture actually is contained a solution to inverse problem for our map. So what are my new variables? So they are, again, principal trailing minors of these three matrices. One of them is just element itself. So those are nicely defined coordinates. They actually can be described in general as, so you can define just what it is. They correspond to fundamental weights in the group. So this principal minors just correspond to fundamental weights. But what are these other ones? So for example, what is the meaning of, let's say, this minor, which starts with x to 3? So you see, I shaded in gray part of these matrices. If you ignore something which is, or everything which is not gray, you will have a reducible matrix, right? You will see this block decomposition. And so I claim that if I want to restore the standard cluster coordinates for standard Poisson-Lie structure, but all I have to do is, well, just again, consider this element, consider just gray part. So there is this square and there is this square submatrix. And I claim that my new function, the strange function in terms of old one, is just a product of these minors in the diagonal. Okay? So, or this one will be a product of this minor and this minor and this minor in the image of our map. So here, this ad hoc definitions that we had before somehow strangely survived this more conceptual definition, and it still works, right? So this gives us a way to construct an initial cluster, and I have to emphasize that in all these cases, the quiver looks almost like the one before. So we had this nice triangular square grid was divided into triangles. The only difference in terms of quiver are some arrows coming on the far side to far left to far right, and far bottom to the top. All right. So what happens if we do have cycles in our quiver? So let me give you another example. So this was the strange name that I gave you, which was called non-aperiodic. Okay, so here's the smallest example of Beloved's interval data where you have this cycle. And we have a similar way of constructing these big matrices. And the trouble here becomes that, well, they become infinite. So our rule is that how they occlude, we take some block of, well, ignore for now these names. I take some block of element of the group of matrix A. So this block contains the lower left corner, and this block contains the upper right corner, and we glue them according to the Beloved's interval data. So if alpha 1 goes to alpha 2, what does it mean? It means that, well, rows of, well, say 1, 2 of one block have to be glued to rows 2, 3 of the other block, and vice versa. So when I do this, I obtain this infinite matrices, and well, if it's infinite, then, well, where is a trailing principal minor? So there is a problem there, but well, we should not despair, because what happens here is that you see this matrices have this nice block structure. They are like block tuplets to diagonal matrices. And so this is what this blocks that I emphasized here look like. And when I have something like that, I can build generalized characteristic polynomials. So I can write something like determinant of well, mu x plus lambda y, right? And this will expand as some functions of x, of my element x. So this is 1 by 1 times lambda to the I mu some k minus what k is to be determined by the matrix. So I have this new function. This will be missing coordinates that I will need, and they will be coefficients for this generalized cluster relation. So in this case, we can still construct a quiver, but it will have fewer functions in it. Okay, and so why is there fewer functions? Because there are new coordinates that are coming out of this generalized relation. So they usually the ratios of these coefficients will be K-inverse for our Poisson bracket. So this construction also allows us to explicitly describe all the K-inverse for corresponding structures. And so this work can still be completed, even though we, for now, just dealing with examples. So let me maybe try to finish with an example of the corresponding quiver. So this is how it will look now. So because of presence of this generalized relations, we lost some of the vertices in our nice quiver, but they will reappear as coefficients of this long relation. But again, quiver looks mostly like a standard one. So in the in all these cases, we can still build a compatible cluster structure. And so this is essentially the end of the talk. But maybe I should now speculate a little bit of why it could be useful to, because well, we all know how to, for example, build integrals of motion and how to show complete integrability of systems that correspond to the standard Poisson-Lie structure, right? There is a well-developed technology, and it's not so clear how to do this for all these other brackets. But now we have Poisson map relating them, all of them actually, to the standard one. And so I just hope that people will look at integrability within this more complicated quadratic Poisson structure, even in the case of GLN. But this extends to other simple groups as well. So let me stop here. Thank you. Let's Yeah, that's pretty much it. Right. Yeah, yeah, exactly. Yeah, and in fact, so what happens here? It's kind of interesting. So what is the meaning of this equation? So when I'm trying to compute an inverse map, so the easiest way would be to find a standard cluster for the well just dense miners for the standard Poisson-Lie bracket. And it turns out that actually this so if you consider this as just equation in one variable, consider its roots. These roots are monomials in stable cluster variables for the standard structure. So you can restore them from this equation. This is the only place where birationality is hurt, so to say. So once we solve this equation, the rest can be restored rational. Yeah, in this case, if we want our cluster all variables cluster function to be regular, yes, you have to deal with generalized clusters. No, it's just it's dictated by combinatorics of the data.